We are so happy to have her here today as a plenary speaker for Math for All, talking about partitions and juggling, a story of unifying parts and seeking balance in mathematics. Please welcome Dr. Pamela E. Harris.
Oh my gosh. Thank you so much, Vanessa. So I got to tell you all that I'm super nervous. And I was thinking, why is it that I'm so nervous? And I was like, because my friends are all in the audience. And so I get to just like hang out with friends for an hour. And it feels like I haven't been able to do that in so long. So thank you, thank you, thank you for putting this conference together, for all the lovely Padlets and ways to allow people to interact. I'm hopeful that this talk will inspire some of you to do some juggling, and hopefully you do juggling together. Okay, excellent. So now that I think everybody can see my slides, maybe some thumbs up. All right, we're good. Let me tell you the story about partitions and juggling, and how those are some mathematical concepts that I have been working on. And I'll take you through some of the juggling history, because as I was learning about some of the mathematics behind juggling, I actually didn't really know a whole lot about juggling. And I actually thought a lot last night about all of the things that we learned in terms of when do we decide that something is mathematics. So this was after the plenary speaker yesterday. And so I thought, wow, what a nice setup, because maybe some of us have not thought about how juggling is mathematics. So we'll talk a little bit about that. And then I'll take you kind of what will feel like a separate journey through vector partition functions. But at the end of the day, these in fact are the exact same thing. And so we'll see a bijection that I'll introduce. And then what I want to do at the end is think a little bit about my own mathematical journey and about the parts that make me who I am, and how I've been trying to figure out how to juggle them all, but really trying to find some balance in the work that I've been doing. So let's get started with some history of juggling. Did you know that the Egyptian wall painting from the wall of Tomb 15 of Beni Hassan actually depicts jugglers? So this is about 4,000 years ago. We also see some juggling in ancient China. And so in this case, you might see some of the objects being juggled here. And so this particular image is part of a mural from the Dahuting tomb of the late Eastern Han Dynasty. And so this is in China, like I said. You also see juggling in ancient Greece. So in the vases or tombs, also in coins, there was actually a lot of acrobatics happening, or games of skill that were depicted. And so you see this particular person here throwing some objects in the air and catching them. We also talk about, what about the first mathematical juggler? You might now go to conferences and actually see people juggling in the lawn. Not any time recently, but maybe in the past, that was an experience you've seen at a conference. You see math folks juggling. Well, the first mathematician who was also known as a juggler is Abu Sa'u al-Kuhi, and he lived around the 10th century. Another thing that he was well known for is having created this perfect compass to draw conic sections. And so here's an illustration of it. I don't know if you can tell too well, but there's, this, like, all these little angles and stuff to draw his compass to be able to draw these conic sections. And then the story that, as I was like reading about juggling, one of the stories that get attributed to him is that before he actually became a famous mathematician, he was better known for juggling glass bottles in the marketplace of Baghdad. And so there we go, first juggling mathematician. Moving to other cultures, let's kind of fast forward now, 1528, the Emperor Babur of Hindustan. So this was the founder and first emperor of Mughal dynasty in India. He wrote in his memoirs that he knew of jugglers who would spin all these rings around certain parts of their body. And so what I imagine, because they're rings, I'm thinking of those days back when I was a little kid and I had a hula hoop, and I was never very good at it, but I could do it with my arms, right? I could never do the waist. Like, I'm just not that coordinated. But I could certainly put a ring on my hand and just kind of spin it. And so now imagine spinning 7 of those rings simultaneously, and not only on your hands, but also on your forehead, on your thighs, on your fingers, and on your toes. So quite a feat of skill. Now, you can also see in this painting by Christoph Weidetz, the Aztecs were known antipodes jugglers, meaning that they juggled with their feet. Because, it wasn't just hard enough to juggle with your hands. Why not do it with your feet? And then I also wanted to, give a shout out to the fact that we got taken from their home country into Europe. And so that's where this painting ended up at. In addition, we can also read about the games of the North American Indian. So this was a book written by Stuart Coolin, and in it, he lists some examples from the Naskapi, the Eskimo, the Achomawi, the Bannock, the Shoshone, the Ute, and the Zuni tribes of North America, also doing all of these juggling games that they would play. And so this is a figure of the kind of balls that they had that they would juggle. Oh, thank you. I do try to stay punny and funny. I see the chat. Okay, so here's another quote that I liked. So Maximilian Prince of Wied, he lived 1782 to 1867. He talked about women being the experts in playing with a large leather ball, which they would alternately let fall between the foot and the knee. So think, we see this a lot in video of soccer players. And the thing that's really interesting for me in this quote is that he mentions women being experts. That doesn't tend to happen historically speaking. We don't get to be called experts almost ever. And so it was very pleasant as I'm doing reading and being like, oh, this quote needs to be highlighted. But not only that, the balls that were being juggled were very neat, great, but also had porcupine quills. So I can imagine that this maybe was painful. I don't know. But anyway, so experts at something that also hurts. Sounds like my life. And so yeah, highlight expert. All right. So what's going on with juggling nowadays? I've given you a little bit of the history. Of course, that is not all encompassing. So I definitely encourage you to do more research on the history of the juggling world. But here's a story that happened around 1947. So jugglers used to hang out with other jugglers at magic conventions. So just like we geek out going to math conferences to see our friends and talk about topology analysis, applied math, data science, all of those good things, well, jugglers would go to these conferences, these conventions. But it happened that in this particular meeting of the International the Brotherhood of Magicians, the jugglers decided, probably over a meal, that their thing was very special and that they needed their own association. And so they created what is now known as the International Jugglers Association, stemming from having attended this Brotherhood of Magicians. And so this sounds familiar, right? We go to JMM and then we think, what would be really wonderful? To have a conference where everyone feels welcome. Hello, Math for All. I mean, I'm imagining that happened, right? Something to that effect, that you have a conversation with your friends and you think, we want to create our own thing. We want to have our own space because we know that it's needed in the mathematical community. And so I just wanted to highlight that this also happened to the jugglers. Okay, so what is the connection between math and juggling? Well, one of the things that we want to think about is we want to be able to communicate with one another. So if Riley and Addie are sharing juggling patterns, they want to talk about how they're juggling, especially nowadays that we're all virtual. We might not be able to see each other. So how do we communicate with one another that the thing that we're doing is potentially a new trick that we've come up with? And so this is the start of where we're going to think about juggling in a mathematical way. So again, just our attempt at being able to communicate these concepts. So we got to set some ground rules. Of course, juggling is not a discrete thing. I get it, my friends, but if we're going to make any sense of anything, we're going to have to put on some restrictions, and I'm going to make juggling a discrete skill. So here's the assumptions we need. So the very first thing, just to get us started, is we're going to think about only juggling a single object because we can only catch one at a time. Okay, so we'll start there. Just a single object. You can only hold one object at hand. And of course, we'll generalize soon. And then we're going to pretend that this juggler is just been juggling their eternity in length. They're just sitting there juggling. We also, to make it discrete and a little bit easier to draw, we're going to think about a juggler only throwing an object to a positive integer height. Okay, so they throw it to height 5, 6, 7, something like this, but never pi or 0.5. The other thing we're going to do is we're going to assume that every instant in time, so for every 1 unit in time, whatever you decide that is, the object lowers in height by also 1 unit. Okay? All right. So with those assumptions, here's our first very simple juggling diagram. So what does this mean? Each of these little arcs represents that at this time I caught the ball and I must immediately release it. And the number underneath tells me to what height I throw it in. Now, because every unit in time represents 1 unit in decay in the height, that means that really I can also count just time that I'll see that object return to hand. Okay, so throw object height 1, catch it 1 time step later, do the same thing over and over and over and over again. And I don't juggle, but otherwise you can imagine, no, I can't do it. I try every time and I'm like, it's going to be so embarrassing. Thank you, Patty. We probably can. Okay, I'm going to try. Okay, that's as good as that's going to get, my friends. Okay. Okay, success. Thank you. Y'all are so supportive. Okay, so what happens if we introduce multiple objects? Here's one such example. So in this case, again, this number is going to represent I have caught an object, in this case, the green object, and I'm going to throw it so that it lands again 3 time steps later. So look at that. 1, 2, 3. Ooh, the green arrives. Okay. But now 1 step after that in time, I catch another object that had been already thrown previously. And so now red object gets caught. I throw it to height 3, meaning that 3 seconds later, again, my time step, I'm pretending is seconds. 1, 2, 3, now I catch it. And then I move 1 time step later, and now I have the blue at hand. I throw 3 later. And now we're back to the beginning because this is the green object I threw when I started. Okay, so 3 objects that we're throwing in the air in this case. And so color coding the arcs can be helpful. All right, here's one where I only have 2 objects and something interesting happens. At a particular time, I actually don't do anything. The objects are completely in the air. So you see that represented by the 0. And so what's happening here? I catch an object blue, I throw so that 5 time steps later, I catch. 1, 2, 3, 4, 5, there's the blue. And notice that immediately catching that, I throw it to height 1, catch, throw long. So there's a long toss, a short toss, do nothing. Catch the other, short toss, long toss. And so all of a sudden you start seeing that there's some kind of nice little patterns hanging out here. And so one question might be, can we describe, if I just give you a sequence of kind of the heights at which I'm going to throw these objects, whether I can actually juggle that sequence? Let's see one where maybe something goes wrong. So here's a particular juggling sequence, which in fact we cannot juggle. Why? Because the main rule that we had set was that at the present time, I can only catch a single object at hand. And unfortunately, immediately I have to catch 2 objects to throw 1 long. And I don't even know what I do because I already, at that point, I'm already out of the game. So you might think, okay, start here. All right, well, I throw this one, but somehow I had thrown a long one. Okay, so this is just definitely not working. Okay, but why not? I mean, the number 2, 1, right? Or the pattern 2, 1 seems so simple. What must be going on here? There's some mathematical thing that we might be able to utilize to figure out whether we can juggle or not. So let's look at another example. So suppose that we were just giving this as the pattern that we're going to throw the objects. So what would you do to try to determine whether 4, 4, 1, 3 is in fact a juggling sequence? What do you think? I haven't showed you a whole lot. So the guess should be to make a diagram, right? That's all we know. So here we are. We're going to need, and also can you tell from this diagram how many objects we might juggle? Like, it's not clear to me if I just look at it, it's maybe because the one at some, maybe this is the one I throw and then I catch immediately, right? So it's not quite clear. It's not, at least to me. I mean, y'all are smart, so maybe you see something I don't. But when I look at this, I'm like, I have no clue. So I just do the thing that we did before. I put my pattern somewhere, and then, oops, I missed a three. I put my pattern somewhere, I repeat it, and then I try to draw the diagram that corresponds to it. So maybe we start here. Let's start with the one, because that's the easy short toss. So I know there I should throw. And maybe just to highlight, let's color code the arcs. So I throw to height one. Then I throw to height three. So there it goes. And then one, and then three, and then one, and then three. So it looks like that object is taking care of the 1, 3. What's happening with the fours that we see? Well, somehow this one comes long and then goes 4, and then goes 4, and then goes 4. So that one gets tossed long the entire game. And then the last one is also a long toss. So 4, 4, 4, 4. So in fact, there's the 3 objects that we're tossing. Now you can imagine that if there's many, many more objects, this might get really complicated. And so there's got to be maybe some algebraic way. And so the answer is yes. We can use algebra here to figure out why, in fact, this thing is juggable. So this is the fun, when you start saying fun words, it's like juggable sequence. All right, so here's how you determine if I give you a set of numbers, whether in fact you can juggle them. So the first thing we need to think about is this thing called the period of that sequence, just its length, right? The piece that repeats. So in this case, we have period 4. What I'm going to do to that number is, or to that sequence of numbers, is I'm going to add 0, 1, 2, 3 corresponding to each of those numbers, right? Or I should say respectively. And my joke here is always never, ever, ever compute in public. And so I type it ahead of time and double check it because I'm always so afraid to add wrong in public. Okay, so to the 4, add a 0, to the 4, add a 1, to the 1, add a 2, to the 3, add a 3. There we go, 4, 5, 3, and 6. And then what you do with this is you reduce mod 4. So reduce modulo the period. And what are our remainders with this new sequence? Well, we notice that we get 0, 1, 3, and 2. So here's the takeaway. You take your sequence, you add 0, 1, 2, 3, 4. Oh, no, to 3, because we're going to go mod 4. Take those numbers mod 4. If these numbers end up being all distinct, in fact, you can juggle. So that's an if and only if statement. So given any sequence, you add the 0, 1, blah, 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 up to p minus 1, where p is the period. Then you reduce. If it happens that all the numbers are distinct, you have just found a juggable sequence. Okay? So that's the main result, or a main result, in juggling. Okay, so now let's do more. What if we could hold more than a single object at hand? Alrighty, let's do that. So that's what's now known as multiplex juggling sequence. And the very first thing is we're going to think about giving a new description of the way we're going to keep track of the balls in air. So the picture to think about here is a conveyor belt. So I don't know if you've ever seen these, in kind of factories where they're just buckets and they keep the objects in the bucket. And then every so often they lower the bucket so you can reach in there. Okay, so here's what we're going to do. The main thing is that now I can have multiple objects at any given height. That's the same thing as saying once that bottom bucket falls down, I can catch multiple objects at hand. Okay, so we're going to set some sort of hand capacity. We'll see that parameters show up soon, but that's just going to tell me the maximum number of objects I can place at any one height. And now to describe how many objects I have at any given height, I create a vector. Vectors are nice because they allow me to give you a number and an index, a position. So in this case, the first entry in my vector describes a number of objects at height 1, 2. The second entry the number of objects at height 2. The third entry, the number of objects at height 3. So this little diagram or this little vector is describing a set of objects at a given height. Now notice this is a kind of screenshot, a picture in time. So to juggle, we need to then see what happens next. So that's what we call then a sequence. Okay, so let's look at that. So here's my example. I start at the juggling state, describing 2 objects, one at height 1, that's that first entry, and then one at height 2, that's that second entry. So what's going to happen one time step later? Remember, everything drops by a unit in height a second later. So in this case, this object is simply going to lower. So you'll see it appear in the bottom bucket. But then I have to decide what I do with this object because I cannot keep it in my hand. I have to redistribute it into some of the buckets. So maybe I do this. So again, the objects are indistinguishable. I can't actually tell them apart. So one of these 2 is this one because it just lowered. And then this one fell to my hand. And then I just happened to stick it in that bottom bucket as well. So now the state that I find myself in just corresponds to the vector with a single entry 2 because there's 2 balls at height 1. Well, what happens one time step later? Both objects fall to my hand and I get to redistribute them wherever I want. So in that case, maybe I put them in this configuration. So 0 at height 1, 1 at height 2, 1 at height 3. And then what's going to happen in the next time step? Notice that I don't have anything that is at the bottom bucket, therefore I can't redistribute anything. Everything should just lower by 1, which is precisely this picture. And so this thing, this set of little diagrams is what we call a juggling sequence. So you transition from one to the other by redistributing objects that were at the bottom bucket. And then you just have to make sure you respect how many objects you can carry at hand at any one time. Okay, so there's some capacity there. All right, so the main motivating question is how many juggling sequences are there? If I specify the starting configuration, so that's what we use S for, the ending configuration, that's E, the length, meaning how many, 1, 2, 3 time steps, how long is the sequence? And again, like I said, a maximum number of objects allowed per bucket. So that number we're going to denote with MJS for multiplex juggling sequence with those defining parameters. Okay, so now that we know the motivation, let's look at an example. So we're going to start with the 1-1 configuration and with the 2 objects at the bottom bucket. We want to do so in 3 time steps. And then because I wanted to just emphasize that the hand capacity is there, but in fact, notice is not really playing a role because the number of objects we have is 2. And so that means that we're not going to see any restriction really being played by M. But of course, if you let this be 1, then the sequence would be different. All right, so let's do some examples. So the first thing I always do is I often draw these first. So my starting configuration and my ending configuration. I place in the other 2 pictures I'm missing, and then I see where I might systematically distribute the objects. Notice that no matter what we do, this particular object will always have to show up in that bucket. Do we agree? Because it just lowers. So this object here is not at play moving from this picture into this second picture. But now this one does have an option. And so what I decided to do first was put it at this height. Notice that that's the highest bucket I could utilize. If I were to put an object in this bucket, it would lower here, and then it would lower here, and then I would not have the correct ending configuration. And so I'm kind of figuring out like how high can I toss first? All right, so that's one juggling sequence. And notice that I also made another toss here. All right, I could also have this. So again, I tossed the first one really high, and then I did the same toss here. So notice this picture is exactly this picture. The only change is here. So instead of tossing this one as high as I could, so I could land where I needed to, I put it 1 bucket lower. And so again, if you're very systematic in how you do these choices, you start seeing these little diagrams appear. And so I won't go through so much detail there, but I claim that there's 7 of them. Okay, so 7 juggling sequences with those defining parameters. And so if you get bored, you can always quiz yourself, write down these parameters and see if you can systematically create all 7. All right, now let's go into a different world, or maybe not. Maybe it's just the other side of a coin. Let's look at vector partition functions. So what is a vector partition function? It is another game that I play in combinatorics. So here's the setup for that game. I give you a matrix that consists of nothing but integers. Okay, that's my matrix A. And then I ask you the following. Maybe Selby comes by and she has a favorite vector, B. And she says, Pamela, my vector is in the span of the columns of your matrix. And I'm like, yay. And then I ask myself, in how many ways, how many x's, can I write a solution ax equals Selby's favorite vector B? In how many ways could I do that? In other words, in how many ways could I express her vector as a linear combination of my vectors, but only using non-negative integer coefficients? Okay? All right. Yeah, I should have used the S for Selby's vector. Why does anybody care about this game? Well, if you're a number theorist, you've heard of integer partitions, and that's the case where the matrix is very well defined to just be positive integers, and you're trying to figure out in how many ways can you write an integer as a sum of other integers. Okay, so yes, number theory people care. I care because I come through from the world of representation theory, computing weight multiplicities, and vector partitions show up there. But you might have seen them if you care about commutative algebra. You might also have seen them if you care about algebraic geometry, or how about discrete geometry? I'm newer to the world of polyhedra, but you can count integer lattice points inside of polyhedra through one of these problems, a vector partition problem. But also they're very, very well studied in optimization. So if you care about integer programming. So they show up all over the place, okay? So no surprise that these are rather famous objects of study. But again, they really depend on a matrix. So if you come by with a different matrix, you can create a whole family of problems. So let me show you a family of vector partition functions that I study. So they're named after Bertrand Constant. So he passed away recently. He was an MIT professor. And all he did, I mean, he did a lot of things, but in this world, he said, what if I picked these particular vectors, which are called the positive roots of a Lie algebra, and I created with them the columns of the matrix A. So now that he specified the columns of that matrix, now we have a vector partition problem that we can play, okay? Now, I could spend, a whole hour going down why this route, but that's another talk. Because remember, our goal is to figure out somehow this is related to juggling. And so I want to get there. But if you're interested and want to learn more, I can certainly send you some readings. And then we can chat on the side. All right. So again, I'm asking you, sweep lots of stuff under the rugs. Let me just tell you what the columns look like. All right. So we're going to start by letting E sub I be the standard basis element of R to the R plus 1. Notice that the index is kind of funky. It's a little off. So this is what we'll call type AR, but it's actually vectors of length R plus 1. All right. So remember, zeros everywhere except a 1 at the ith entry. All right. I am going to create a new set of vectors. I'm going to call them alpha sub I, and they're just going to be consecutive difference of those standard basis elements. Okay, so a 1 and a minus 1 consecutive in the vector, and then zeros everywhere else. Then I'm going to put those vectors together. Now, keep in mind, are those linearly independent? Just the alphas? Are those linearly independent vectors? Ooh, linear algebra. Silence. Let's think about what would happen if they're linearly independent. So they are. If they're linearly independent, how many solutions am I going to have to AX equals B? And B is in the column space of the matrix. I'm going to have a single solution. So it's not very interesting to create matrices whose columns are linearly independent, because then the counting problem becomes a 1 or a 0. That's not fun. If you're trying to count objects, it's like, well, I mean, I guess there's cases where having 0 or 1 is a good thing, but not in this setting. So we want to create a column that has a lot of linearly dependent vectors so that something interesting happens on the count. And so in addition to throwing in these linearly independent set of vectors, I'm going to go ahead and I'm going to throw in a whole lot of things that are linearly dependent by creating them as linear combinations of the ones that are independent. But I'm going to do it in a very strategic way. I'm going to do it by only taking consecutive sums where the things, right, all the subscripts are consecutive. So I could start at 1 and end at R, but they must all show up in between. Okay, so alpha 1 plus 2, that's okay. But I couldn't do alpha 1 plus alpha 3, not allowed. All right, so now with a set of what are known as positive roots, highly dependent set of vectors, I am going to now create a matrix, and that's going to be the matrix that we use in this vector partition problem. So the best thing to do, because R can be really big, let's look at some very small cases and consider what happens. So let's look at A2. So again, the length of the vectors is 3. It's always one more than the subscript we use here. So those are the vectors alpha 1, that's 1 minus 1, 0. Alpha 2, 0, 1, minus 1. And then I add them together. So if you add together, again, I don't add in public. It's right there. Okay? And then I just grab those and put them inside of a matrix. And that's the matrix that is defining this vector partition problem. So again, Sylvie comes by. Here's a vector that's in the column space of that matrix. And then my job, Pamela, is going to count the number of ways that I can express Sylvie's vector as a non-negative integer linear combination of the columns of the matrix A. So if you want, you might almost think, well, this is, oops, that's so thick. This is dependent on the matrix A. Okay, so you could also think about it that way. So if we change the matrix A, that's a brand new game. For every matrix you give me, that's a different game. All right, so what's the actual answer? Well, I claim that the number of ways to express that vector simply depends on which of those two numbers is the smallest, and I throw in a 1. So take the smallest plus a 1. So why is this the case? Well, let's think about the objects I had that I could use in writing the vector B. So I had the object alpha 1. I also had the object alpha 2. And I also had the object, which was the sum alpha 1 plus alpha 2. And so now what could I do, meaning what numbers could I put here that are non-negative integers whose sum actually gives me n1, n2 as coefficients of alpha 1 and alpha 2. So let's do this again. Think back to the juggling. You have to do this very systematically. So what I'm going to do is maybe the first choice I make is I say, you know what? I'm going to use this 0 times. Well, if I use that one 0 times and I want the whole thing to sum up to n1 alpha 1 plus n2 alpha 2, I better use n1 columns alpha 1 and then n2 of the alpha 2s. That's one possible way. Well, okay, maybe I use one of these alpha 1 plus alpha 2. And in that case, then what happens? Well, I have to restrict because I already used one. And maybe you already see the pattern. I keep doing this, and how big can this particular number get? If I want these coefficients to always be non-negative, the biggest I can put here is precisely the smaller of the two. So this better be minimum of n1 plus, comma, n2 of these alpha 1 plus alpha 2, and then you subtract the rest. Yeah, I'm going to be lazy. Okay, the corresponding thing there. So how many did we see? Well, you start counting at 0 and you go to the minimum. That means you have the minimum plus 1. And so again, that was kind of an example, but the proof is you just count how many times you use this vector. And you can use it at most, the minimum, and then because you started at 0, you get in that plus 1. Okay, So look at that. We have a complete characterization of the partition function in type A2. Not too bad, right? Like we could do this. We could have done enough examples to kind of get a gut as to what the formula might be. So then the next thing you might do is say, okay, great, let's continue forward. And let's now make, instead of A2, let's make A3. In that case, you have alpha 1, alpha 2, alpha 3, the sum alpha 1 plus alpha 2 plus alpha 3, and then the sum alpha 1 plus alpha 2 plus alpha 3. So there's my positive roots. I throw all of those into a matrix, and then I ask the exact same question. Give me a formula for the number of ways to write an arbitrary vector in the column space of that matrix. So I gave this problem to my students at Williams a few years ago. And then I said, okay, and I showed them basically what I've shown you, nothing more. And then it was like, hello, here you go, Professor Harris. And I was like, what is that? Like, why did that get so complicated? That looks not, that it was so much better in A2. And I thought, well, maybe if you make some conditions, pick some numbers, see if maybe you relate these coefficients in some way if this formula simplify. So they went away, they came back, and they gave me this, which I thought, oh, okay, that looks definitely much better. At least I don't have to compute any minimums. I also don't have to compute any sums that depend on the minimums. Okay, great. And in fact, as a sub case, if you have the condition that the coefficient of alpha 1 and alpha 3 are bigger than or equal to the coefficient of alpha 2, a nice sequence of numbers arises. So you get some tetrahedral numbers showing up. And I thought, okay, that's great. But you see how complicated this is getting. Well, that's because there's actually no general formulas known for these families of vector partition functions. In fact, those decompositions, those choices that they made for where the coefficients live, it was just shown in 1964 that you could create some conditions on the coefficients that resulted in each of the formulas being polynomials of a given degree. But knowing how you make those choices and what the formula is continues to be a complete area of research study for very, very many people. So, okay, well, you can't give formulas. And somehow this is connected to juggling. Let me show you how. We already know that there's only 3 vector partitions for this object. Remember, the minimum of the coefficients plus 1, so in this case is 3. Here they are. The one where I use 2 alpha 1s, 2 alpha 2s. I use a single alpha 1, a single alpha 2, and then the sum of them. And then where I use 2 of the ones that come alpha 1 plus alpha 2. So these are really multi-sets. Okay, so when I write 2 alpha 1, I mean there's 2 objects of alpha 1. Okay, now let me show you a juggling set. So here's 3 multiplex juggling sequences that start and end at the configuration of 2 objects at the bottom bucket. They have a hand capacity of 2, so only maximum 2 objects per bucket, and they have length 2, 1, 2. Okay, there's 3 of each. 3 is a small number. So that's not a coincidence, right? Like, it's just like, okay, it just happened. Like, who cares? Yes, you showed me 3 partitions and you showed me 3 particular juggling sequences. Okay, so we stare at these numbers and then you try a different example. So here's a different example. We plopped into the OEIS. What happens if you start and end at configuration 3? You let n be the time step, so we're going to increase the time step. And then we force hand capacity 3. So we saw these numbers show up. And if you don't know this, you should put it under your belt somewhere. Take a note. OEIS, the Online Encyclopedia of Integer Sequences, fuels a ton of my research. Because if you plop a sequence in, it might tell you how it's connected to something that's already known. Or you might not find it, which means that you found a new sequence and then you get to add it into the encyclopedia. Okay, but look at this. These are the exact same numbers that show up when computing 3 of this vector. So if I vary n, I see 1, 4, 20, 112, 660, and it matched perfectly. And so now you have a lot more intuition that maybe there's something here that's more interesting. So here's where we go into a bijection. So because I like working on math with people, I talked to my math friends about this problem and I showed them what I showed you. And so I said, Caro, Chris, Alejo, Anthony, I'm stuck. There's something here, but I can't quite figure out why these numbers match. Now, I might not have a formula, or maybe if I have a formula, the formulas match, but that doesn't tell me how these objects are related. So we wanted to give a bijection between these combinatorial objects. And so here's a result. So we were able to show as a preliminary result that if you take n copies of the vector, that's the sum of all the alphas, and notice here's r, so that's the length of that vector, r plus 1. That's the exact same thing as the number of juggling sequences, which start with the objects at the bottom bucket, end with the objects at the bottom bucket. You have a hand capacity of n, and the length of the sequence is where these two parameters match. And in fact, we were able to do this. This was kind of like our initial first proof based on the conjecture that I had. We were able to do this in complete generality. You tell me a vector, and I can fiddle with these parameters to make the count match up. And so here's how that's done. This was the key insight into the entire argument. Anytime that I am in the juggling world, I am throwing objects. Every time I throw an object at some time to a given height, it encodes one of these alphas. And remember, the alphas were sums of EIs, right? So let me just do this quick example. So look at what happens here. This is time 1, okay? Time step 1. What happens? I threw 2 objects at time E sub 1 minus, what am I supposed to do? Keep the subscript I, add the height I threw. So should that be a 2? 1 plus 1? And then I check, because I said I wasn't going to compute in public, and here we are. Here we are. So somebody give me some thumbs up if that's okay. So 2E1 minus E2. But remember, this is just alpha 1. Look at that. And then if I continue, what happens here? This is time 2. So I have 2 objects. There's 2 balls that I'm going to throw. I throw at time 2 to height 1. So 2 plus 1. Oh, that's exactly these. And if you do this systematically by keeping track of when you throw, to what height you throw, and encoding that particular vector, you have a bijection between these combinatorial objects. And so, like I said, we could do this in complete generality, absolute complete generality. You give me a vector, I can then tell you from that vector how to actually encode the starting state, the end state, the hand capacity, the length. And with that bijection, we can show then that in fact, it was not a coincidence that those numbers were matching. These objects have the same number of them. Okay. It doesn't mean that it has helped me in the counting. I just know now that juggling is just as hard as vector partition function problems. So for those that are juggling, it's like juggling is hard. Not only really physically hard, but mathematically very difficult problem. Okay. All right. So let me go into this last bit of the talk here. So I want to talk to you a little bit about unifying parts and seeking balance in mathematics. And so I've been thinking a lot lately about who I am as a person and how those things end up affecting whether I feel like I belong to the mathematical community. And so being a woman, Latina, queer, an immigrant, first generation, a mother, partner to a military veteran, all of those things are my identities, parts of who I am. And so for a long time, I never felt like I fit in. And so what I started doing, I was always just trying to find people that in some way had some similar background to me so that I could collaborate with people that I felt like I could just be me and not have to hide certain parts of me. And so I wanted to highlight some of my Math for All family who are in the audience or are part of the conference. because they've been an important role. They've played an important role in who I am and that I can continue to be myself around them. And another thing that I started also thinking about was part of my job, right? There's all these parts. I teach, I do research, I do service and outreach. And I also started to think about how I might begin to unify them. And so one of the things that I started working really hard to do is to maximize things at the intersections, all while focusing on working with people who were in my math family. So I got involved and helped create Latisms, so Latinos and Hispanics in the mathematical sciences. I also have the pleasure to work with Rebecca Garcia this summer again at MSRI Up, where I get to do a lot of research with undergraduates and bring in a whole new set of people into our math family. I also helped co-found and run Math Swagger. So this was a workshop last summer for graduate students so that they too would have a family that they felt like they belonged to as they were going into these graduate programs. And maybe they were going to be really isolated, possibly the only underrepresented minority in their program. I also thought, you know what? I feel like I have things to say about what this math community is like. And so with my wonderful friend, Dr. Eris Winger, we started a podcast where we just get to chat and tell it like it is. So check that out. And then we thought, in working with undergraduate students, there's always all these questions that I take for granted. Like, if you're going to your first math conference, what should you wear? How do you network? What do you do? What are all these obstructive rules in math, these norms that we don't talk about? So we're organizing a webinar doing this. Or what about the fact that Latinos continue to be underrepresented in mathematics? Let's build a research community. And so some of the folks that are in the audience are going to be leading some research groups to really, again, build community. That's really the key part here. And then I started writing books, right? So it's like you talk, you write, you do all of these things because my goal is to make sure that other people can succeed in mathematics as their authentic selves. But then I thought, I'm working a lot and I'm trying to find some balance. But the issue is that it's not about seeking or finding balance. That's really the wrong word, my friends. It is about creating balance. You create balance, you don't find balance. And so when we're juggling, the first thing is that less can be more. There's going to be times where you're asked to do things and you need to decide whether you can continue to add additional objects to your juggling sequence. Think about your hand capacity. And you should do it at your own pace. You get to determine the length of your juggling sequence. So don't go at other people's paces. Do it so that you can succeed. And also, it is always so much better when you get to juggle with friends. So if dropping balls is something that's inevitable, the one thing that I leave you with is that you must continue to persist. Okay, so keep that in mind, that it's going to happen. There's going to be some objects you drop. The first thing is you might not need to pick them up, okay? Or they might not break. And so persist, persist, persist as you continue in your math journey. And I want to just end with saying, thank you, Math for All, for the opportunity to come and share some math and some joy with you this morning. And stay in touch. And I'm happy to answer any questions you might have.